So we are in LTE. We are talking about LTE features, new features, and I mean we already talked about 2 or 3 of these, but I will go back again. The data rate is 326 megabits down. That's quite a bit up from whatever we had in 3G. However, this is with 4x4 MIMO and 20 megahertz. The modulation goes all the way up to 64 QAM. That's another improvement, and that's how you get all these high rates. OFDMA. Now, OFDMA, they use only in the downlink, not in the uplink. WiMAX, the main difference between this and WiMAX is WiMAX used OFDMA in both. Okay. And so we will see when we come to SC-FDMA, I will explain what SC-FDMA is and why they chose that. So other than that, it's mostly similar to WiMAX. Hybrid ARQ. So that's the term we didn't define last time. ARQ is automatic repeat request, right? That is means another word for retransmission, right? Automatic repeat request is the telephony word for timeout and retransmission in the IP world. In the IP world, when we have a TCP and then it times out, you retransmit it. That is called ARQ here, but this is hybrid ARQ because generally the retransmission is done at the MAC layer. Here it is hybrid, MAC and PHY combined. So I have a slide on that as well. How do you do retransmission at the MAC and PHY combined? Then frame sizes. This is another big difference from WiMAX. I am not teaching about WiMAX, but if you know about LTE, you know everything about WiMAX as well. So one difference is the frame sizes in WiMAX were bigger a little bit, and the telephone companies complained that this may not be good enough for whatever they were doing. So they selected small frame sizes, and it will become clear as to what the frame size is actually, 10 millisecond and 1 millisecond. So that means there is a fast turnaround. If you need something, you can get it within 10 millisecond and 1 millisecond of when you wanting it. In WiMAX, it was few more milliseconds. Persistent scheduling. And so in WiMAX as well as in LTE, every time, in every frame, every station is told when they can transmit. Okay. So when I send a beacon, I mean, when the base station sends a beacon, it says that station number 3, you can transmit at this time, station number 2, you can transmit at this time, and that's it. Basically, nobody else can transmit. And station 4, you can receive at this time, station 5, you can receive at this time. So there is a whole scheduling done, every frame. So persistent scheduling is that you can be scheduled forever. I mean, forever is actually not true, but basically you can schedule for longer time than just one frame. I can say, okay, like every third frame you can transmit in the 4th slot. Okay, so that is persistent. So why it is good? Because then I don't have to tell you every time. I save some bits in transmission and you are always ready, you know when your turn is. So that is good for repeating things like voice and video. Where once you start watching the video, you're going to transmit or receive every 30 millisecond or 33 millisecond a frame, right? IP-based flat network architecture. And the phone company knows that its architecture is too complex with all these boxes, Visa, you know, like Visa, BTS, BTC, SSG, SGSN, GGSN, and so on and so forth. So, okay, let's get rid of everything and just make it simple IP. So we will see that too. So all of these words, actually most of these words which are in blue will be defined in the next few slides. Yeah.
So when you say that OFDMA is used in Africa as well, when you talk about WiMAX, isn't that a concern for the battery of the device? I mean, when you talk about mobile devices, we need to factor in that power available is very less, and OFDMA takes a lot of power.
No, hold on. I'll hold on to the thought that OFDMA takes a lot of power. No, it doesn't take a lot of power. That is not the problem. Why did you think that OFDMA takes a lot of power?
Just for the fact that OFDMA is peak to average ratio is pretty high.
Okay, so that is coming up. Peak to average ratio is coming up later on in the slides. Okay, so hold on to that thought then. That peak to average doesn't mean that the power is high. It's just slightly different. All right, so we move on to that. Actually, this right here, and it will show up. So the way OFDMA works is, we have explained to you in many different ways, but I have not shown you this diagram, which is important to understand how this is implemented inside. So at the base station, these bits are going to user 1, these bits are going to user 2, these bits are going to user K. Right? Each user's bit goes through a coding, FEC, forward error correction coding. All right? So that is where we add more bits so that if something happens, we can correct it. After that, we do the QAM modulation. So then we decide, whether it is 64 QAM or 16 QAM or how it will go for this user, right? Every user has a different modulation. Then this is done serial to parallel. So all these things, all these symbols as we call them now, are parallelized. So first one goes here, second one goes there, third one goes there, fourth one goes there, then fifth one goes there, and so on and so forth. So just, they become parallel. Okay, as shown here, 4 in a parallel, but there might be more than 4, okay? And so all these users. Now this one, at this point, we might have, let's say, 1024. Let's just assume that we are using 1024 subcarriers, right? So we don't just put these users on the 1024 one by one, we just randomize them too. So this one might go here, second stream might go there, and so on and so forth. So this is subcarrier mapper. So what that means is that these are your subcarriers, but the one that go on the air may not be in the same order. Okay, the order is randomized in some way. Actually it is a fixed mapping, but basically the first carrier may go there, second carrier may go there, and third carrier, and so on and so forth, right? So that way, if some noise hits some carriers, it doesn't hit the same user. All right, the noise is distributed among many different users because now the users are all over on this side. On this side, so this is actually M to M or L to L mapping. That means the number of channels coming in here, carriers coming in, is exactly the same as number of carriers going out there. And so it's just different order. Enter? It is just like interleaving. In some sense, yes. Interleaving is generally used for bits in the time domain. This is in the frequency domain interleaving. Okay, in some sense, in the time domain, you take the bits from this and this guy and then mix them together. That is interleaving, right? So this is frequency domain. And these are all frequencies, and these are all frequencies coming out. Clear? All right. Then we do IFFT, L point IFFT, which basically means whatever number of carriers you have, that number of IFFT, inverse fast Fourier transform. As a result of that, whatever comes out here, you do parallel to serial. Now you serialize it. So now this looks like one bit stream or one waveform stream, whatever that is. All right. And you add the cyclic prefix and you send it off on the air. All right. So notice that everything starts as a serial and goes out as a serial, but in between we make all these things parallel and randomize them and so on and so forth. Now when it comes back, the opposite is done, exactly opposite of this. So first thing we do is we remove the cyclic prefix, do the serial to parallel, do the FFT, instead of IFFT we do FFT, do the demapping, we had mapped it here, do the demapping. Now the bits are actually in the order of the user, so we just have to worry about one user here now. On the receiving side, we don't have to worry about user 2, 3, 4, let's say this is user 1, so it just takes the bits that belong to it. Okay, and then does the frequency equalization. This was not there on your slide. Frequency domain equalizer, FEQ. FEQ is the frequency domain equalizer. So basically what it is now you are going to do the demodulation, and you need to know what the channel was and so on and so forth. So for these carriers, whatever the amplitude and the phase was, so basically we do that equalization. This is basically what is called channel estimate. So for each carrier, we know what the channel did to it. Okay, it reduced the amplitude by this amount, it changed the phase by this amount, and so on and so forth. All that is removed. So now you have good estimate of what you have received, and then you do parallel to serial. So that is the opposite of this. Parallel to serial, now you do the demodulation and you get the bits back. Okay. So this is the reason I have to explain, and one reason that you have to understand is that in the last time when we had this research seminar, somebody asked us to, if you have to change your frequencies every few microseconds, don't you have to change your radio? No, nothing in the radio is changed. The radio receives all 1024 on every user, on every phone. You receive all 1024 subcarriers, right? It's just that which one you have to receive is in the map. So they are mapped here and they are demapped here. That map is transmitted in the frame, transmitted, beforehand. So you know which are your carriers. So then you use it. If your carriers change, this map will change automatically, and there is no more extra work to be done in anywhere. Now what these are all mathematics. This is all mathematics here. IFFT, FFT. This is all, matrix multiplication and things like that. Okay. So whether you are doing matrix multiplication by 1024 non-zero numbers, or you are doing matrix multiplication of 1024 with some zero numbers, doesn't make much difference. Okay. So yeah, go ahead.
The fact that you're receiving all of this other information that's not necessarily pertaining to you, does that have any bearing on energy efficiency?
No, that's what I'm saying. See, this is exactly the point, is that energy is consumed in the radio part, right? Not in this is basically, the radio part is where the energy is consumed. When this thing goes into the radio, into the antenna, you transmit the energy, right? And when you receive, once it goes inside, then it is basically some numbers which are being sent from here to there. Okay? So that is one thing, is that the any matrix multiplication is same size in the receiver and the transmitter. This is a 1024 FFT, IFFT, and in the receiver it is 1024 FFT. The only difference here is actually that difference is even not there. Actually, I was thinking there is a difference here. So this is exactly the same. Only after the FFT is done, we just take our own bits and leave everything else out. This is like Ethernet. In the Ethernet, you can hear everybody's frame. Okay, all the frames that are coming to the same wire, actually we don't use the wire anymore, but technically you can hear everybody's frame if connected to the same wire, but you just take your frame out and leave everybody else's out. Right? Yeah, question.
So the first block is for the uplink, and the second one is for the downlink, yes?
So, hold on. So the first one is the transmitter at the base station. So transmitter at the base station means transmitter is high, right, on the mountain. So that would be the first set of diagram is for downlink. Yeah, okay.
And the second one is for uplink.
Now hold on. No, it's not for uplink. Second one is the receiver at the mobile. This is still downlink. Right? This is the downlink transmitter. This is the downlink receiver.
The same as the up.
Well, it's coming up. Up is coming up in a minute. Because remember I said OFDMA only in the downlink. First, this has to be clear as to what these modules are and what happens inside. Because if you don't have concept of this, then then different kinds of questions come up. Like they came up in the presentation last week in another place anyway. So it's clear that everything is transmitted, all the carriers are transmitted and all the carriers are received. The carriers are randomized for different users are mixed in. And then basically each user may have their own modulation. Somebody may use 16 QAM, somebody may use 64 QAM, and so on and so forth. And then basically there is a lot of serial to parallel. I haven't really shown here the radio part. So this is all the digital part. Right? After this, it goes into the radio where there's an amplifier and, this is analog part. Right? I haven't shown you that. That's where the cost is, that's where the energy is. So what happens in that part is that we have something called amplifier, power amplifier. Right? And the power amplifiers take the power in and send the power out. So they amplify. You might send 1 volt and get 4 volts out. Okay? But they're not linear, they're slightly non-linear. So what you do is you just use a small part of it and it looks like a linear in that part. If you use the whole thing, then it will be non-linear. Right? And so if you want a linear amplifier, it costs a lot. If you want to have it for a very small part, it's cheap. If you want longer part, it's more expensive. If you want for much longer part, it is even more expensive. Now in OFDM, each carrier is modulated according to a specific channel condition. So if this carrier is going through an area where there's a lot of noise in that frequency, then it will be modulated with a different amplitude and phase, right? Then something which is going through a very nice area, amplitude can be low and still make it. Okay? So that means there is a lot of variation of power levels of carriers. So this carrier is here, this carrier is there, this carrier is here, this carrier is there. So that is where this peak to average ratio comes in. So the peak to average ratio is high. If you take all the carriers and take the peak and you take the average, the ratio is high. Alright, this is called pepper. High pepper. And high pepper means you need high cost amplifiers. Right? Because amplifiers and blah, blah, blah. All right. So we can afford such amplifiers in base station, but not in mobiles. Now, this is a controversial statement. Why? Because those who support WiMAX, like us, would say this is meaningless. Come on. It doesn't make a difference. But those who wanted to kill WiMAX, this is the biggest thing in the world. Okay? So this happened. Qualcomm won. Intel lost several $1 billion in this game. Okay? And Qualcomm made several $1 billion in this game. These are not cheap games. Okay? So there is a lot of this thing goes on in the industry. Okay? And as a result, LTE doesn't use OFDM in the downlink. Yeah, they don't use in the uplink. Sorry. All right. So what do they use? They use single carrier, FDMA. Good old days. Okay. Single carrier FDMA is that you get this frequency band, you get this frequency band, you get this frequency band, and everybody gets the frequency band. And then in your little frequency band, the noise pattern may not be very different. Right? So the amplitude may not be that different. And so now you will be able to use cheap amplifier. Now you have given something and lost something. So you got this low pepper, but what you have lost? You have lost the noise resistance. right? Because if the noise is there, you got killed, everybody else is fine, happy. And so the thing is that whole distribution of noise over, that we call it interleaving in the frequency domain, that is gone. Okay, so every user gets a band, a small piece of the frequency domain, and then they just transmit in that domain. Okay, you still transmit. Basically, it is very similar to what you were doing before anyway, but now instead of being all over, you have a particular domain. So this is how the transmitter looks like in the uplink. You take the user bits, you do the FEC like we did before, you do the modulation like we did before, and you do the serial to parallel. And this is where things become different, and that's why I've ellipsed it. Now, instead of doing whole 1000 by 1024 IFFT, you take these things and you do a small FFT, and so this multi-carrier becomes, basically this becomes FFT, and now you put it contiguously here, M right there. Okay, second user will put the next one. For you, rest will be 0, and then you do the parallel to, you do this your L point FFT, and then you do the parallel to serial and you send it out. It's not very different. If you compare with this diagram, previously this was not there. Right? Now at the receiver at the base station, when they get that, they do just the opposite. Serial CP, SP, L point FFT. So you did this FFT, then you did the demapping. Now in the demapping, everything which is, basically this band goes to this user, this band goes to that user, this band goes to that user. So they're all contiguous. That's the main difference. All these frequencies are contiguous for each user. Okay, they do their equalizer as before, and then they do their little FFT, IFFT here, parallel to serial, detect, you got to get. There was a lot of controversy whether this really reduces pepper, how much pepper, and whether pepper is important. Every point is very controversial. Okay, and I can tell you exactly how they lost billions of dollars. Intel lost billions of dollars, and how they made billions, they made multi-billion dollars. This is a very big industry, very big market, and the companies try their best to get their way around. Anyway, so this is the difference. So this is single carrier FDMA. Now you notice that this looks very much like OFDMA. What we did was, before we did put into the IFFT, we coded it already. All right. So this is called pre-coded OFDMA. Pre-coded OFDM. By the way, this book is very good. I recommend this book. This is actually happens to be a Safari book. And this guy Ghosh, I worked with him when I was at WiMAX forum. So he wrote a book on WiMAX, which I liked very much. Then he moved on to LTE. Everybody moved on to LTE. So he wrote a book on LTE, which I liked. And actually he wrote a book on LTE Advanced. I haven't seen it, but I think it should be good. So all of this detail actually is from that book. Any questions about this? So you understand the difference between uplink and downlink, and you understand that this is really the difference. In the uplink, it is pre-coded OFDMA, which is called SC-FDMA, single carrier FDMA. Where is the single carrier? You won't see it because there is no single carrier. Still it is multi-carrier, right? But it is single carrier in the sense that when you start, it looks a single band. Okay, so that is about the FFT part. There is another change And I don't know whether this is the difference between WiMAX and LTE or not, but I think this might be in both. This might be in both, but I have told you about STBC, space-time block code, back when we talked about waveform propagation. It was module 4. And we said that if you have multiple antennas, then instead of sending different information on different antennas, if you send something on one antenna and something related on the second antenna, you can do much better in terms of correctly decoding it. So what you do is, if you have two antennas in two time slots, on the first antenna you send S1 in time slot 1, and on the second antenna you put S2 on time slot 1. In time slot 2, which is just following slot 1, basically, you will be sending minus S2 star on antenna 1 and plus S1 star on antenna 2, where star is defined as complex conjugate. So X plus IY, the complex conjugate is X minus IY. So what is X and Y? Basically, X is the horizontal part, Y is the vertical part, and X, IY is basically, because everything has a phase, right? So if you draw it in a 2-dimension, you saw those points in the QAM, right? So they are expressed as X plus IY. Horizontal part and the vertical part. Sine theta and cosine theta. Okay, if the amplitude is A, then A sine theta would be, I think, vertical part, A cos theta would be horizontal part, something like that, right? So theta is the phase. So you put every symbol as a complex number, and you do the complex conjugate, and sometimes you have to multiply with minus, in which case it will be minus X plus IY. Okay, and with some mathematics it can be shown that this is much better, and this is called space-time block code, because we are doing space. Space is here, antennas are spaced. Okay? Space is antenna and time is here. Time 1 and 2, and so this is called a space-time block code. This was invented by Wahid Tarrok, 1998, and it's basically started a whole new series of STBCs. This is not just 2 by 2. You can have 2 by whatever number by whatever number you want. Whatever number of antennas you have, whatever number of slots you want, you can design something. Okay, so there are extensions of it. Yeah. Oh, of course. The question is whether this arrangement, like minus S2 star and S1 star, can you arrange it some other way? No. I mean, basically, for every particular size, there is an optimal arrangement. If you arrange some other way, you will get less. So this is the most optimal for 2 by 2. So antenna seems to be? Antenna seems to be arranged in a linear way. S1, S2 you mean, or S2, S2?
If you look at the router or whatever.
I look at where?
I mean, if you look at the router basically or whatever.
Router? I'm sorry, specifically, what router?
I mean, this one. Yeah.
This one, yeah. Okay, this is a base. Let's collect a transmitter. Okay, whatever it is, right? Okay, transmitter, yeah. Look at the transmitter.
It seems to be arranged in a certain way, basically, because what I know about antennas, they can be arranged in a linear way. You can arrange them in a circular way or whatever you want.
Okay, so you have to explain all that. I don't know what that is. Any other question? He's saying the antenna can be arranged in a circular way, and I don't know that, so I'm not going to get into that one. Okay? All right. So same thing, instead of doing on the time, you can do on the frequency. So here's the thing. So we want to send 4 symbols, X1, X2, X3, X4. And now we can send them in this manner. We have X1, X2, X3, X4 and their stars, which means complex conjugate, and we can send two of them on one frequency, the other two on the other frequency, the other two on third frequency, another fourth frequency. So we are sending 8 symbols on 8 symbols on 4 frequencies, right? And instead of previous diagram, everything was on one frequency, single carrier, right? In this diagram, we are doing different carriers, right? So this is a space frequency block code. Instead of space time, it is space and frequency. So on one antenna, there are 2 antennas here. On one antenna, we send this combination. On the other antenna, we send this combination. Okay. You can also do it many different ways. You can do like this, as shown here, where X1, X2 star, X2, and X1 star are like this on 4 different carriers. Here they were on, just like if they were a single, this one, right? So there are ways to arrange these symbols and their conjugates. Again, we don't need to get into the details, but the idea is that this increases the noise resistance. Now you are in a much better position to decode these symbols correctly, okay, than without doing this coding. It doesn't increase the rate, you see, because you are sending 2 symbols in 2 time slots. So you basically, didn't get any rate increase because you have 2 antennas, doesn't matter. But with 2 antennas, now you have much better probability of getting those 2 symbols correctly. Same thing here. You have 2 antennas and you have 4 subcarriers. You're still sending 4 symbols, but you will get much better. Okay, so this is called SFBC. Space Frequency Block Code. So basically, this is how STBC is done on OFDM. Yeah.
What's the difference between SFBC and STBC on each subcarrier?
Yeah, so basically what it is when you do STBC on multi subcarriers, then you get this. Basically, you are dividing the things on different subcarriers. So here, you see, all we did was X1, X2 star. So what we are saying here is that we are going to do X1 in the first time slot, X2 star in the second time slot, and we are not going to do on the same antenna, and we are not going to do in the same subcarrier the other one, which was X1 star and X2 star. So this is basically mixing frequency as well as the time and the antenna, actually, in some sense. So we have 2 antennas, 2 time slots, 4 subcarriers, everything is mixed in. Okay, 4 subcarriers. Here, we didn't talk about any carriers at all, just one carrier. So that is basically time. So in some sense, this is a special case of the next case where, we have multiple subcarriers. So here we are putting them, and there's a special way, there's an optimal way of putting these. So I'm not going to take you through the mathematics of matrix multiplication and figuring out, which symbol should go where, and then how do you figure out that this is the right symbol which came out. So there is a way to optimally put these signs, and the stars have been put in some optimal way.
No, I was asking what's the difference between the first one and the second.
Oh, what is the first one, second one? Okay, so you see, this is what will go on a single carrier, right? And now it is going on 2 different antennas on 2 different carriers. Here, this is going on 4 different carriers. That combination, X2 star minus X2 star X1 and X1 star X2 is on 4 different carriers. Whereas here it is 1 here and 1 here, 2 carriers. This one is a little bit more mixed in. And this one helps if the channel changes fast. So basically, you don't have to wait till the second time slot to decode this. You can just decode it in the first time slot. Okay. Now, these are very complex concepts. I'm just giving a very simple explanation of these because when you go to read these books, you'll find all the math. Right? All right. Now, the next concept is puncturing. Puncturing we have done before, but we didn't explain in detail maybe. So basically what you do is you take some bits and you say, I'm going to put forward error correction on this. So you make twice as many bits. So D1 and D2 is the data bit. And now we added 2 more bits, E1 and E2. So this became D1, D2, E1, E2. 4 bits. Right? This would be called 4 by 2. I mean, basically you're transmitting 4 bits for every 2 bits. Right? But then they say, well, there's no need to send everything. Most likely they will make it anyway. So they do 1/4 puncturing. Means that we will not send 4th bit or 1/4 bit. So they, in this case, they decide not to send E1 and they will just send D1, D2 and E2. Okay, this is called puncturing. So this is 1/4 puncturing, or this basically we wrote it 3 by 4th code because for every 4 bit we send only 3 bits. Okay. Now, when you get at the receiver, you don't know what the 4th bit was because they dropped it already before transmission. So you put some R1. R1 is not known, right? You put an unknown there. Now, because you have a code, you know that since you have a code, that code will tell you what should R1 be. You can correct the errors, right? So it can correct that and it can say, well, R1 should be that. And then you can get D1, D2 with very high probability. All right. Now, they have proven it mathematically that it is much better to do this 4-bit coding and then drop 1 bit than to just do a 3-bit coding. I mean, they could have just gone from here to there, 3 by 2 code, and then not have to do this R1 business, but they found out this is better. Question?
Is there like an intuitive explanation for that? Or is it just is there like a complicated
No. So the thing is, first of all this coding requires polynomial calculation, which we do actually. The thing is, we do that when we do CRC in 473. I don't know how many of you did the polynomial division in CRC calculation, but I do it in my class. Okay. The same polynomial division is used for all of these coding that we are talking about. Okay. But most of you have not done that, I suppose. And so I'm not going to take that right now. It is, but basically, so just you have taken my word for it that puncturing with a larger code is better than, shorter code. Yeah.
Is it always E1 that's dropped?
No. I mean, that's another math, and I'm not going to go to that one. So puncturing is not just, like that, right? Because the receiver has to know what has been punctured out. So there will be some kind of communication that, okay, I have punctured out the 4th bit, or, 3rd bit or whatever, so that they put it in the right place. That thing. Yeah.
And also, I think that it increases the data rate. Yes?
It does increase the data rate.
Yeah, and I mean, if you want to choose between the E1 and E2, which one do you draw? I think it's just all the time fixed. I mean,
it's fixed, but what is the question is, that's what I said. It is fixed because the receiver will not know if you just drop 2nd or 3rd. Yeah. Then not only you don't know which bit was dropped, you don't know, where to put R1. Right? So that position is fixed, yeah. Okay. If not a question, then we come to the next point, which is ARQ. ARQ stands for Automatic Repeat Request. And basically, this idea is that you transmit if it is received, packet is received in error. And so what you do is, in IP, and actually in TCP as well, that you send the data. If the data does not make it, then you send a NAC. And if you get a NAC, then you send the data again, and you get the ACK, then you're all set. NAC is optional. If you don't send the NAC, the sender will time out and will send it. That will take even longer. So NAC saves you some time. All right. So what is wrong with this? What is wrong with this is that now the whole data has to be sent again, and the previous data is discarded. So somebody figured out that if we keep the previous bad bits and get the new bad bits, combine them, we might be able to get good bits. Right? So that's what we do. We send the data with half puncture, and this guy could not make anything good out of that. So it says, sorry, I didn't get it. Then it says, okay, all right, here are half of the bits that I took away. Half puncture means I took out 2 bits, and now I'm going to send you one of those 2 bits. Because he is not sending the whole data. He's just sending some of the part of the things that it had kept. Now you might be able to combine and decode. Now with 3/4, you are able to do it. Not twice as many bits, but just, actually, I think we have to do some calculation here. But only 3/4 of the punctured bit, actually, you're able to do it. Something like that, but less bits than before. You see what I mean? Now, if it doesn't make it a second time, what will it do? It will send the other 1/4 bit that it has kept. Right now, you got the whole bit set. Figure it out now, what is there, right? If you don't make it, then maybe I will send you the whole thing all over again. Right? But most of the time, with one retransmission, you might be able to do it. Now, notice here that puncturing is not a MAC function. It's the phi which keeps it. Right? So the phi has to know that we are retransmitting, that we have to, there are the punctured bits. Let's send those punctured bits. This is why it's called hybrid, because the MAC alone cannot do this, and the phi alone cannot do this. It's the hybrid. It's both combined. Now, there are 2 ways you can do it. This is one way. Second way is that you just send the data again. Now, second time, some other bits are bad. This time, these bits are bad. And sometimes you know which bits are bad because this bit is really not clear whether it's 0 or 1. Everything else I know because this bit is like halfway between 0 and 1. Right? And here on this side, this bit I know is 1, but this bit I'm not sure 0 or 1. You can combine those 2 and take the good bits. Right? So, one alternative is to combine the good bits of multiple transmission. This is called chase combining, a type 1 HARQ. This is called incremental redundancy, a type 2 of HARQ. So even if you send the same bits all over again, HARQ goes back into the phi. Thing is, because here the thing, the MAC doesn't know which bits are good or bad. Basically, what happens is that phi knows that when it is translating this analog to digital, it knows that this one didn't come out, all right? And what normally it happens in most of the other networks that we know of is that if some bit is bad, the whole packet is thrown away and the MAC is told the packet is gone, something like that, right? And they just retransmit the whole thing and they redo the whole thing and the previous packet is thrown away, right? So now the phi is keeping the previous packet and the new packets comes in, it compares the bits and says, okay, now I can take only good bits out of these. Right? So this is why it's called hybrid ARQ. Okay, is this clear? Yeah.
So the type 1 is just sending the whole data twice?
Yeah. That is allowed too. The thing is, type 2 would be better, more efficient. Yeah. And type 1 is less efficient, but both are allowed. And I really don't know. But what happens is that when you write the standard, some people say this one and that one say, okay, like both are allowed. And so I don't know which one is really implemented or not, right? But both are allowed. Yeah.
Is it generally considered bad practice to consider or to combine layers like this?
Okay, all right. No, hold on. So this is, layering has advantages, layering has disadvantages. So the advantage of layering is that when you're designing Mac, you don't have to worry about phi. You can design your Mac as it is. And you can design your phi without talking to the Mac guys. Now, having said that, that's the advantage, the design time. But if the two teams can get together and work out something, so this will work for this particular Mac and this particular phi. And so now, yes, the disadvantage is that now if somebody brought their own Mac, it will not work on this phi. If somebody brought their own phi, so on and so forth. So there is this thing, but then the argument is that when do you bring another Mac on the same phi? When you make another Mac, you make another phi. So while the layers are all designed independently, at the end of the day, they are just tied to each other. Right? So there is an argument on each side. And so this is an optimization. And what is happening is that many of the things that we learned in the wired networks are being broken in the wireless networks just for every single bit. You see, here every single bit is important because there is only so much spectrum and we want to send as many bits as possible through that spectrum. Right? Alex is sleeping behind you.
So this is more of like an after-the-fact optimization rather than like an initial design decision?
Well, okay, hold on. So what happened is, this is not after the fact. What happened is before LTE was designed, lot of people in the academics published these papers, and it is better to do this way. And then LTE guys said, okay, all right, in this LTE we will do this. So, for example, this may not have been done in GSM. I mean, GSM actually doesn't have retransmission anyway, and they were not designed for data anyway. But I'm just saying that so previous technologies may not have it. Now, if the technology comes today, so WiMAX does it, LTE does it, LTE Advanced and everything else will do it now because people found out that there is a significant advantage. So it all starts with some research and this and that, and so it's not after the fact. I mean, it is after. I mean, it is not really after the fact because this was in the original WiMAX, and I remember going through this whole hard discussion. So if you go to our website, you will find some papers on performance analysis, this and that, of ARQ versus hybrid ARQ. Okay, ARQ would be simply, not doing any combine, just do data mag, data attack. That was the previous thing, that most of the previous technologies before WiMAX did this. Yeah.
Just another question. With the kind of retransmission of the bad bits in the hybrid ARQ, does that require a whole nother frame? Like you have to have the
packet, yeah, right. So basically what will happen is these bits will be sent to the same user and it will indicate that this is, retransmission of HARQ of that previous frame that was there, right?
It's just a smaller payload than it would be.
Yeah, right. Good. Now, second thing LTE tried to do was that they said, well, let's get rid of all these boxes, as many boxes we have, and simplify it. So in 2G, we saw this one, we had SGSN and GGSN. Remember for data, SGSN and DDSN. In 3G, we still have them, and then this was called RNC. In LTE, now we still need actually some more boxes. In particular, we have these 4 boxes here, 1, 2, 3, 4 box, but everything goes on IP. So that's the thing, is that even voice goes on IP. And that actually causes some problem, and I think that probably was changed later on. I don't know that, but I mean, I'll have to check that out. But basically, initially it was all data stuff, right? So everything goes to IP, but goes through these 4 functions. So what are those 4 functions? Serving gateway. So SGW, this is serving gateway, and this one between the radio access network and serves as a mobility anchor when the terminals move. Now, this is something that needs explanation. What is a mobility anchor? And one important thing that I have skipped in this class, and I should not have skipped, but there's not enough time, is mobile IP. The reason I skipped it because nobody uses mobile IP. But the concepts are important. In mobile IP, what happens is that when you go away from your desk, your packets which come to your desk are received by your assistant, and the assistant then sends you the packet to your hotel where you are. It's like a phone call. Your phone number doesn't change when you move. The phone call comes to your office and she says, okay, I will connect you to Mr. X, and she forwards the call, or he forwards the call to your hotel. So that person is a mobility anchor. Okay? Mobility anchor doesn't move. You move, but the mobility anchor stays there and he knows where you are. And every time you move, you tell the mobility anchor, look, I am moved from Hotel Marriott to Hotel Hilton, or whatever. And now your phone call will go to the new hotel. Right? So the mobility anchor is the point which stays fixed and allows you to move. This is mobile IP. Actually, this is basically everywhere else too. I mean, like, we have this HLR, home location register, which knows, Okay, so anyway. So that is serving gateway. That is serving gateway's function. Your phone calls, your data part comes to there, but you're now going from tower to tower to tower, from location to location, and it goes there. Packet data gateway is basically just looks, and this is the end of your IP world. Packet data gateway. This is the end of your IP. So everything else that we need to do before we send you on to the wireless is done here. And so it termination of the evolved packet core towards the internet, IP services, address allocation, deep packet inspection, policy enforcement. What is deep packet inspection? Deep packet inspection is security firewall. So all the security stuff that needs to be done before we take you in on this side, I put you out on the IP side, that is done here. This is the boundary point. Mobility management entity. Mobility management entity does everything that the anchor doesn't do. So basically, it keeps track of roaming, handovers, tracking, anything that needs to be done for people. So for example, anchor will not tell you which tower to connect, but MME will tell you that, okay, you are on this tower, but you're moving north, so now you connect to that tower. Right? For network initiated handover. And we told that there are two kinds of handovers. The mobile initiated handover, in which case the mobile measures two towers and says, look, I am getting bigger signal from this tower, so I'm going to move to that one. And then the MME will move you to that one. In the other case is that the MME somehow, knows that where you are moving to and tells you that there is a tower there, please connect to that one. So MME job is to just do this handover thing. And policy and charging function, which is very important in the phone business, that is the PCRF. Yeah.
But at this point, I think the time is SC-FDMA. Okay,
so okay, let me see. This one you are saying, is it SGW or what?
SC-FDMA.
Yeah. I mean, so I didn't put it here. Same thing, yeah. You can put SGW. And sometimes I've seen S-GW, sometimes P-GW. So, but that is the same thing, yeah. MME. So now they have added 4 new boxes. I don't know whether really it adds, it helps. So this is flat. This is the best they can do in terms of, making it IP as well as the old thing. It turns out that making LTE IP based doesn't really reduce anything because everything old is still there. You cannot get rid of 2G. Okay, this picture you have seen before. So every LTE system has 2G, 3G, and 4G, and LTE. right? So the previous boxes have not gone away. SGSN, GGSN, SS7, SGW. This is what you're talking about, SGW. Is that what you're saying? Yeah. So those boxes are all there. SGW is here too. S-GW, SGW. Okay, anyway, so now it is becoming even more complicated. And we had seen this slide too, so I'm going to skip that. Now, unless there are any questions about those boxes. But anyway, so next we come to the frame structure. How are the bits sent on the air? So just like we saw in GSM, there was a super frame that consisted of a frame and so on and so forth, right? The same thing is done here. There is a super frame which is 10 milliseconds long. So this is super frame 0, super frame 1, super frame 2. So each of these is 10 milliseconds long. And for some reason, they don't call it frame. Each super frame consists of subframes which are 1 millisecond long. Okay? So now this super frame consists of SF0, SF1 to all the way to SF9. 1 millisecond long. Each subframe consists of 2 slots, which is half millisecond long. During this slot, you can do the downlink. During this slot, you can do the uplink. Okay? Now, during these, you can send symbols like this. You have a symbol and you have a prefix, right? Cyclic prefix. So this is symbol 0, 1, 2, 3, 4, 5, 6 symbols. And then there is a gap between the 6 symbols, which is called the prefix. So in this case, if you have 5.2 microsecond gap here and 4.7 here, so 1, 2, 3, 4, 5, 6 times 4.7 is like 30, somewhere 30 microsecond plus 5, 35 microsecond. You subtract that from this and you get the symbol size, you get these sizes. Then there is one thing called extended cyclic prefix where there is more gap, in which case only 5 symbols will be sent, and the gap is 16 microsecond. Why 16 microsecond? Because if you're going long distance, you need longer gap. If you're going short distance, you need shorter gap, because what the gap does is it allows you to do multipath. You know, if something went straight and something went like this, they will still not kill each other. You know, so this is how much path difference can be. 15 microsecond or 4 microsecond. Now the difference between the first and the second 5.2 and 4.7 is, because if you do 4.7 for all of them, you're still left with something in the beginning, and we said, okay, so that is, yeah, I mean, obviously, right? So anyway, so the important thing to notice is that the downlink is 0.5 millisecond and the uplink is 0.5 milliseconds. So if I want to talk, I mean, or let's say you want to talk and I'm the base station, you will say, look, I want to talk. So you will say that in the uplink, right? And within half a millisecond, I can turn around and say, okay, all right, your turn to talk. So this is advantage of having a very short, what we said, frame. Remember we said WiMAX had a bigger frame. WiMAX had a bigger frame, and then the phone companies complained that no, this is not good for us. We really need real time, and this one is scheduling. So we want to turn around very fast. So they selected a very short frame. Again, there's an advantage of very short frame and there's a disadvantage of very short frame. Advantage is you can turn around very fast. Disadvantage is that you turn around very fast. I mean, you just have to keep turning around. So that's the thing, is you're dancing, like this. So that's each side can have the win, but this side won. LTE won. All right. Now, what happens in that half millisecond? Half millisecond is this slot, right? There are 1,000 carriers or some number of carriers. Each user is given some number of carriers over certain number of slots, okay, certain number of time, right? So minimum you can get is 12 carriers over one time slot. 12 vertical, 7 horizontal, 7 symbols horizontal. Actually, we saw only 5 symbols, so I don't know. Yeah, these are 7 symbols. Okay, there are 7 symbols right there. Right? So, minimum I can give you, or minimum the base station can give anybody is 12 by 7. And we will, if you need more, then we give you 24. If you need more, we give you 36 carriers and so on and so forth. So we don't go to 1024 in a 1 by 1 carrier. We just go into units of 12. Makes accounting easier rather than doing complicated stuff. All right, so 12 by 7. It's called resource block. So when time starts, then right in the beginning there is a map. There is a map which says that, okay, this resource block belongs to that user. You have the resource block 5 through 27, so you will get this whole area. And then the user 2 has this area, and so on and so forth. And if your name is not there, then you don't have anything in that. This is both for downlink and uplink. There's a downlink map, there's an uplink map. All right, the map actually only comes in the downlink direction. What happens is, in the downlink frame, there is a downlink map that says that if you get this whole frame, this is your bit, this is your bit, this is your bit, this is your bit, right? But also says that in the next uplink, here is the map. So the uplink map is in the downlink, right? And it says that, okay, when the next frame comes in, you can transmit at this frequency at this time, you can transmit at this frequency at this time, you can transmit at this frequency at this time. And this changes every frame. Okay? Unless you are doing persistent scheduling. Right? For some users, they will get persistent scheduling. Right? So for them, every 4th frame, you get this particular thing, and then you got that until, for how many frames we have given you. So this is how the resource allocation is done. Okay? Yeah.
So if user have 12 subcarriers,
minimum, 12 minimum. You can get 12 times 10, 120, and you can get 12 times, whatever,
at each time slot?
Oh, yes, the thing is, this is the minimum. Resource block is 12 subcarriers over one time slot. So basically 7, these are all symbols. So 7 symbols, 12 carriers. Right? This is the unit of allocation. Right? So when you are making a map, you know exactly where how many blocks are there, because there will be otherwise too many blocks and too many points. This is another whole thing. If you go back to our paper list, and you will see our paper list somewhere on our website, to give the allocation optimally, you have to fill in with rectangles. You have this whole rectangle to fill in, and every user has a different requirement. So this bin filling problem is a very interesting scheduling problem. Because you get a rectangle, you get a rectangle, you get a rectangle, and how do you fill in so that everything is used, right? Now, if the rectangles had one very, very tiny, there will be a lot of possibilities, right? So we said, okay, this is 12 by 7 is the minimum. Yeah.
The second will be 24 by 7 or 24 by 14.
4 by 7 or 24 by?
The first one is the minimum 12 by 7.
Uh-huh.
If I need 24,
yeah,
it will be by 7 or by 14.
Okay, so the question is whether it is better to go in time or better to go higher. If I need more, better to go higher in time or better to go higher in frequency? This is a very interesting question. On the downlink, it doesn't cost anything extra for the receiver to receive 1024 carriers. It is already receiving all carriers, right? So in the downlink, it will save the battery if the time is less, carrier is more. Right? Uplink is just the opposite. Okay? In the uplink, if it was using more carriers, it will probably need more batteries. I mean, I don't know how this all works, but basically, so the uplink, you really want to minimize put all the power on few carriers. Okay? And save the battery. So, yeah, so it is done horizontally in the uplink, vertically in the downlink. And this is a very complex problem, and we can write papers and papers, and I have a paper in IEEE transactions and special. So this is really high quality transaction, right? So a lot of work there. How to schedule these squares inside a square. I mean, these are not squares actually, rectangles inside a rectangle. Okay. All right, that brings us to the end. And with this thing about WiMAX versus LTE, if you go back 5-6 years ago when I taught this course, there was no LTE, everything was WiMAX. We taught WiMAX. Then in 2009, WiMAX went away. So I think 2010, we had half and half. Now we don't talk about WiMAX anymore. So what is the difference? They are very similar with minor difference. And the difference is net head versus bell head. This is very interesting. There are two kinds of networking guys. One which are net head and one which are bell heads. Okay? Bell heads work for the phone company. The net heads work for the IT companies like Cisco and, Facebook and things like that. They think very differently. And actually, most of us actually came as a net head. Enterprise networking versus carrier networking, academic versus telecom. Most of the academics are in this IP business. Okay? Intel and Google versus Ericsson and Qualcomm. So these guys are pushing WiMAX and these guys are pushing LTE. Both use OFDMA. Both are incompatible with 2G and 3G. So one of the things that LTE guys said, no, WiMAX is not compatible with 2G and 3G, but so is LTE. Come on. Right? And both are basically, now they have gone from quad band to pentaband. And so anyway, so there is very little difference, but done is done. WiMAX is gone, LTE is here. That's the summary. 5 key points. 4G IMT advanced requires, well, I didn't talk about 4G, so I'm not going to, I think the first point probably will be good for the next lecture. We will talk about 4G. That requires 1 gigabit per second, which LTE cannot deliver. So WiMAX and LTE are 3.9. And they have numerous common features, many bands, flexible bandwidth, FDD, TDD, MIMO, beamforming, HARQ, IP-based OFDMA. These are all same. The key differentiator is SC-FDMA, which is pre-coded OFDMA. STBC requires transmitting. So now we know the difference between STBC and SFBC. STBC is space-time block code. Now we have a space frequency block code where the blocks go on different frequencies. We know puncturing. Puncturing means you just don't send some bits, all right, and save the bandwidth. And then you send it if you get into trouble. That is called HARQ, hybrid ARQ. Right? And then we saw the super frames and the frames and so on and so forth. Is that every half a millisecond, the things changes. Okay? Now, if you go back to WiMAX, the numbers are much larger. I mean, half a millisecond would be considered too small in the WiMAX world. And but what is done is done. So this Ghost book is very highly recommended. Then these are all the other books. I haven't indicated, this is Safari book for sure, and I checked it this morning. I will have to check whether these are still in Safari, and this is not a book anyway. These are something that you can download, these two. These last of three things are not books anyway. All right, enough on the Wikipedia. And then if you want to read more, there are lots of books on LTE. That's the end. Any questions?